Okay, before I do these sets of notes here, I just want to do a quick recap of some of the stuff we should have learned this unit. Essentially, we should have learned about 3 types of functions. You're going to learn about so many more. Ultimately, though, this should put your list at 4 functions. I need you guys to know how to write a linear function. In general, if you want to write a linear function, the most common form of something linear would be like y equals mx plus b, right? Kind of from last year. Then we learned about how to write quadratics. And quadratics you can write in a whole bunch of different formats depending on which one kind of suits you best. One of the formats would be in like a general form. It would be like an ax squared plus bx plus c. Good old standard form. What's so great about standard form? What can it help you figure out just like that? Yeah. It's pretty hard to write an equation in standard form, like if you have to work backwards though. So another good format to work with would be like a vertex form, and a equals h minus, like this sort of mess. That one's kind of nice because if you're given a vertex, you can plug the vertex in right here, and then the only thing you're missing is your a value. So if you have any other point on the graph, just plug in x and y and solve for the a value. Another way of writing something in quadratic form would be like a factored sort of thing, where you have a leading coefficient. Maybe write it as like x minus, I don't know, p x minus q, where like p and q are the intercepts. So those are some generic ways of writing an equation if it's in quadratic. So this would be your good old linear graph. This would be your quadratic graph. Then we talked about some extra ones that only you guys have, which would be like an absolute value graph. But in a way, the absolute value graph is very similar to the quadratic graph, where you have like an x minus, I don't know, h plus k, because these values inside here just kind of move around where the point of your absolute value is. Does that make sense? That's the one I was just doing with you, hey? So, I mean, absolute value kind of functions very similarly. And then we can actually do the exact same sort of thing for a reciprocal graph, which would have like this sort of shape to it. I would write it as y equals a, and then maybe write it as like x to the minus 1. And again, if you just know your leading coefficient, even if you don't know the leading coefficient, all you need is an xy pair, and you can find that leading coefficient. Those are kind of like the generic formulas we'll use to try to write an equation. For those of you guys in my physics class, you know how we've been doing a lot of graphing recently? The one extension that I'd like to get into soon, we just haven't done, is I'd like to actually write an equation for the line you just drew a line through. Like you guys know how you kind of calculated the slope of the gravity on that one there? In theory, we should be able to write an equation for that. Y equals, what'd you get for your slope? 11.4. Okay, so y equals 11.4x plus b. Right? Now that you know your slope is 11.4, how would you find that b value? Well, pick any other point on your graph, plug in the x's and y's, and that would solve for your y-intercept. Does that make sense? Right, and so you should, in theory, be able to write an equation using data, and that's like the important link then is between the maths and the sciences. Is if I give you the information on the graph, if you can write yourself an equation, then you can type that into your graphing calculator and do so much more powerful stuff with it. Does that make sense? So we just haven't, I haven't made you do that yet in physics, but we probably will. Okay, anyways, let's talk about today's notes then. So the last thing I want to talk about are what are called the inequalities. And essentially what I need you to be able to do now is take all of the graphs that we've learned about, which normally have an equal sign in their equation, right? Every single one of these things I just wrote there, I wrote it with an equal sign. Well, what if it wasn't an equal sign? What if we wrote it with one of the inequalities? Do you guys know these guys are called the inequalities here? Equalities are literally equal signs. The inequalities are the greater than, the less than, the less than or equal to, the greater than or equal to. You guys familiar with those symbols? We're going to talk today about how to deal with it. What if it's not an equals? What if it's greater than or less than? And there's a couple of different rules for how you do this. So I'm going to break it up into 2 halves here. If there is one variable, like just x being greater than 2, there's one way of solving it. If there are two variables, there's actually a different method of solving it. So it depends on whether it's single variable or multivariable that you're working with. You've seen this different. Kind of my written notes here. You know how we've been solving for solutions, where you try to figure out what x is equal to or y is equal to, stuff like that? Well, inequalities don't have a solution. They have what's known as a solution set. Because there's not just one answer, there's not just two answers, there's an infinite number of answers. Let me do the example here. Let's say I give you the inequality x being greater than 0. Well, what values of x are greater than 0? Well, there's so many, right? 1 is greater than 0. 2 is greater than 0, right? I mean, but you can get into the ridiculous. 900 is greater than 0. Decimal numbers, those are greater than 0. Does that make sense? So, because of the fact that there's now not just one answer, there's like an infinite number of answers. Like we have now there's not a finite, you guys know that word? Yeah, instead of infinite, it would be finite. Since there's not just one or two or three answers, but there's infinity answers, we have to represent them visually. So today, all of your answers are either going to be on a number line or what's called a solution region. I'll show you this one more time. So here's some examples. Maybe you've done this before, maybe you haven't. But like, we can answer these on a number line. If I said that x had to be less than or equal to 0, you'd draw a number line, like so. On 0, you'd probably put a dot, and you'd fill in the dot, by the way. We talked about how a filled in dot means that you count that value, whereas an open dot means that you don't count that value. You heard that before? And then you just draw an arrow saying, well, everything on this side right here, that's less than or equal to 0. If you want greater than -2, use an open dot and draw the arrow the other way. So the key now, though, is how do we work with this with our linear, quadratic, absolute value, and reciprocal graphs? So that's my next few slides. Let's just try an example. I want you to solve this. There's not going to be one answer. There's going to be an infinite number of answers that work. For example, 7 might be true. But 8 might also be true. And 9, and 10, and 11. Right, does that make sense? And so we're going to have to represent this on a number line when we're done. So the best way of solving this is just to pretend that it could be an equality. Just pretend that it's an equal sign for right now. So temporarily just say, okay, well, 3x plus 4 equals 2x minus 4. Pretend it's an equal sign. This would give you how many answers? 1. Okay, that's okay. We'll just deal with that for now. So minus 2x from both sides, minus 4 from both sides. You'd end up with x equals minus 5. Here's how I like to show this. What some kids might then do is they might say, well, that just means that x has to be then less than minus 5. Because all you have to do is just pretend that this was still there the whole time. This was still there, and this was still there the whole time. Does that make sense? And that works 9 times out of 10. But there's a very obscure rule when it comes to working with inequalities that you probably learned once in your life and you forgot. The rule is whenever you divide by a negative sign, you have to flip an inequality. You heard this before? And based on that really obscure rule, my advice is don't try to just leave this symbol in there the whole time. My advice would be just leave it as just x equals minus 5 right now. Now what we're going to do is we're going to do what's called a test point. I'm now going to write my number line. So I'll just put like minus 5, minus 4, minus 3, minus 6, minus 7. And minus 5 is kind of my critical point in the middle here. I'm going to test one side or the other and figure out whether it's true. If values on that side are true, then hopefully all the values on that side are true. And the values on the other side of this test point are hopefully false. Give an example. Give me some number that's lower than -5. Any number lower than -5.
-6.
Perfect. So all I'm going to do is just go 3 with -6 and 2 with -6. I'm just going to test this out. 3 times -6 is minus 18. Add 4, it's actually minus 14. Okay, now to this side. 2 times negative 6 is minus 12. Add one more, it's actually negative 13. Is negative 13 greater than negative 14? Apparently, negative 6 would be true as my test point. Well, based on this logic, then hopefully minus 7 should also be true, and minus 8 should also be true. And everything on this side over here should be where the values are that I'm looking for. Let's say that you just randomly chose the other side though, right? Like I started with the lower than side. What if we picked a number that's greater than negative 5? So give me a number that's greater than negative 5.
1.
What did you say?
1.
Even better than that? 0. 0 is actually the smartest one to use. I use 0 every time as my test point, by the way. I mean, don't get me wrong. It should work for 6 or 7, but do you guys see why 0 is going to be the best number to use? If you plug in 0 for this and 0 for this, is 4 less than negative 1? It is not. So therefore, if 4, or if 0, which would be way over here, is not true, then negative 1 should not be true. Negative 2 should not be true.
You are a smart person.
So the advice I give you, just pick 0 as a test point. With one exception. If the point in question itself is 0, then pick something else. 0. 1. Yeah. So the best point is to pick your 0 and 1. So, anyways, this is how you demonstrate it. You demonstrate it with like a number line. If I do need to write it out then, I would say that x had to be less than minus 5. Which honestly is what we had right here. Just the only reason I suggest doing this is that little tricky negative dividing flipping inequalities trick, which maybe you've heard of before. This just, it solves that problem. You just don't have to worry about it. That make sense? Oh, one more thought. I left this open because this was not or equal to. If it was or equal to, you'd color in the dot. Okay, well, that same logic then should apply to quadratics. If you wanted to, I guess, you could try to leave this symbol sitting inside this thing the whole time. But hopefully you'd agree, isn't that just making life really complicated? I don't see much purpose in that. So just temporarily pretend that it's an equal sign. If this were x squared minus 2x equals 3x plus 6, how many answers would you have? Probably 2. Maybe 1. Maybe none. So let's solve it. You have x squared minus 5x minus 6 equals 0. X plus 1, x minus 6. There's our values of x. Kind of breeze through that part. You guys able to handle that? Okay, well now here would be the issue then. You know how this one right here was this symbol right here? I don't know that it's really fair for me to keep that symbol going through here the whole way, because going from this step to this step right here, I think you guys all intuitively just get how to do that, but I'm not sure that it's fair to keep that same symbol going through there. Oh. So here's what I'm going to suggest instead. Make a number line. These, when we get to calculus, by the way, I have a name for these. We call these critical points. So I may as well use that terminology now. These are known as your critical points. So I'm going to plot those on the number line. So negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 30. So I'm going to plot 6 on here, and I'm going to plot negative 1 on here. Should I fill them in?
No,
Why not?
no. Because they're not filled in.
It's not an or equals to sign. Right. Well, you know how in the previous graph, when there was 1 point, it was like this side or this side? Well, now what ends up happening is we actually have 3 regions to the graph. We have this section right here. We have the middle section, and then we have like the top section. So rather than testing just one side or the other, I kind of have to test all 3. So let's start with the easiest one though. The easiest one will be the middle section for testing. And the reason why the middle section is the easiest to testing is because 0 lies in its section there. And 0 is the easiest number to test, right? Because if that's a 0 and that's a 0, this side's all 0. And if that's a 0, is 6 greater than 0? Okay, since that's true, all of the numbers in the middle section where 0 is true should also be true. So I'm just going to kind of fill that in with like a line, but it doesn't get to continue for forever because that's kind of like the bounded in section. It's the section that's kind of bounded on both sides. But all the values in between here should work. I do need to now check the other two sections though. So I need to check a number in this section right here. Unfortunately, 0 is not going to work. So, hey, come on, you got a question?
I have a question.
Yeah, come quick. Just give me 1 sec to give these guys a task to do. Can you guys take -2 as an example? Plug -2 in for all the x's and see whether the statement is true. And then when you finish that, you know how you have to do like the top side right here? I just pick 7. And see whether or not the statement is true or not.
I'm really struggling with this question. For,
4B?
yeah.
Oh, okay. So you gotta convert miles per hour and kilometers in minutes. We just need to make them consistent. 4B or 4C?
4B.
Oh, the one you have written here?
Yeah, I didn't know I was getting really confused if I had that.
Okay.
If
Like here's what I do. I do 2 kilometers per minute. And then like I do what you did here, you do minutes per hours. So that works really good. And then I find the ratio online of miles to kilometers. Did you like Google that somewhere or find that somewhere? Right? Because then really what happens is that one cancels there, that one cancels there. And the only units you have left are miles and hours. The last thing you gotta do is just a whole bunch of math. 2 divided by 10 times by 60. You could divide by 1. You could times by 1. Divide by 1.6. And I'm guessing that gave you
you got
7.5. Okay. So then since it asked which one was lower,
so that
and then that one's lower.
okay. So I did.
You absolutely did it correct.
Okay.
That's exactly what I said.
Really melting my brain.
No.
Yeah, this chicken one, because that's when we had that sub and I was trying to, he was trying to help.
Yeah.
And so I didn't know, I just multiplied the 3.61.
Yeah. So here's how I read it then. I'd go like it was 3.61 dollars per kilogram. And then so I don't want kilograms, I want to put it into pounds. You see to the ratio, I believe it's 2.2 pounds in a kilogram. So I'm going to say 2.2 pounds in 1 kilogram. So I think you did this incorrectly then, because you should take 361, you should actually divide by 2.2 pounds in a kilogram.
Okay.
Which is going to make it a small number, which means that it's way better than this one. I mean, this one still was better, but it's actually like 361, it's actually like $1 something.
Yeah, I tried, then I got really confused, so then I started doing everything, made this number multiplied and divided, and then I
Try both ways.
the other numbers.
And that's really kind of like what we did today, where all you gotta do is multiply it by how much you can get your head around that. It's actually not that hard.
I was really confused because the number was so low, so I just thought.
Yeah, the comparison here is really not fair. I mean, if you get the option of this per kilogram or that per pound, that per kilogram is way better. You're paying less for more, right? Because a kilogram is a bigger unit than a pound is, right? And then here you're paying more for way less.
Okay. Okay, thank you.
When you guys tested -2, I'm guessing the statement wasn't true. And when you tested like a number like 7, it also probably wasn't true. Okay, so here's how we would end this then. You could write it like this. Another option would be to say that -1 is less than x, which is less than 6. You guys see how like I'm writing it where -1 is the lowest it gets to, and 6 is the biggest it gets to, but I'm not going to use the or equals to sign because, well, I didn't have one up there.
Oh, I get it.
What?
Took a while.
No, we're good. Okay.
Hey, you guys all smart physics people. Physics. You know what I'm getting physics right now too? I'm failing 90.
Okay. So this next note here is about how there's sometimes multiple regions. You know how like on this last graph here we had like a section here, a section here, a section here. The more you get into this, the more you've got to have multiple regions. When you guys take calculus at some point, it's often common that you'll have 3 or 4 or 5 different regions to test. So that's what I have right here. So I want to show you what's called interval notation. I hinted at it very briefly yesterday in our notes, but I didn't want to take too much time because I was low on time. So I want to explain how interval notation works today, if I get a moment, which I believe I have notes on it on the next slide. So can we do the next slides, and then we'll come back to more of this. Here's how interval notation works. It basically goes, tell me the lowest number you have, tell me the highest number you have. That's it. If you use a square bracket, it means you get to include that value. If you use a rounded bracket, it means you don't actually get to include that value. So let me go back and show you how to use the previous examples in what's called interval notation. You guys agree that the lowest you got to is -1, the highest you got to is 6? Okay. In interval notation, you would say the lowest number you have is 1, the highest number you have is 6. But since you did not get to include either -1 or 6, you don't use round brackets. You use rounded ones. If it was an or equals to 1, then you change it to square brackets. In theory, it's actually possible to have like 1 rounded, 1 squared. That can actually show up once in a while. We're not to that point yet. You will get there eventually. Okay. One more thought. Because of the fact that this looks like the coordinate point 1, 6, where this is an x and this is a y, I like to try to have my kids write this in front of it, d, implying this is the domain. Because if you just leave it as a bracket, you might think that it's the point -1, 6 way up here, and that's not what it means. It's a completely different notation. So let's talk about how to do this one here, though. On the one on the previous slide, what is the lowest number you can get to? Well, when you're kind of groaning going, it's because you can always keep going lower. So the convention for this one would be the lowest number you can reach is -infinity, is how we'd write that. Basically, you can go to infinity, you can keep going bigger and bigger and bigger. You guys know the infinity sign, right? Like a sideways 8. And then the largest number you can get up to is -5. But since you can't actually include -5, you use the round bracket. One more thing. When you're trying to figure out what bracket to use on -infinity, you always use a round bracket. The rationale being that -infinity is more of a concept rather than a number. So you can't actually include infinity itself because it's not actually a value. It's more of a idea that like, well, it's the biggest number you can imagine. Let's try a few more examples here. Let's find the solution set for x² + 4 being greater than 0. So here's how we solve this. Let's say you need x² + 4 to be equal to 0. Alright, how do you solve this then?
Subtract 4 square root.
That'll work. I'll subtract 4, I'll square root. Hang on a second.
Just kidding.
Bless you.
Actually, that's not bad. I like your idea. Can we find an x value that doesn't work? Can you find an x value that would plug in here to make that somehow work? Well, if you plug in 2,
I get
2 squared would give you 4. When you add 4, would it give you 0?
You can't square anything and add to it.
Yeah. If we were to graph this, by the way, x² + 4 would look something like this. Where is it gonna be equal to 0?
Never.
I don't think it's ever gonna equal 0. So for an example like this is a bit more challenging. The question then is, where is this greater than 0? Is it everything gonna be greater than 0? Or let's just test some numbers now. If I tried 0 right here, 0 + 4, well, that's bigger than 0. How about 7? 7 squared, that'll give me 49 + 4, that's bigger than 0. Well, negative numbers. negative 100. Negative 100 squared would give you 10,000 plus 4, and that's bigger than 0. So if we were to draw a number line for this, I actually don't even have a critical point. And the answer for the number line would literally be everything.
Greater than 0.
Or less than 0. Literally everything would work. Because even negative numbers, right? If you picked negative 12, well, negative 12 squared would give you a plus number.
Yeah, great.
So we already have a notation for this though. Do you guys remember what the other notation for every value of x would be? Because every value would work. Here's another way of writing it though. What's the lowest number that would work? Negative infinity. What's the biggest number that would work? Positive infinity. And then just put curly brackets around it. That's another way you could write your solution set. Because literally everything would work.
You know, the infinity sign trips me up. I don't know, I like mine are always so messy. I have to write.
Oh. Yeah, I guess you could just do that. Turn it sideways, draw an 8. Okay, let's talk about this one here. If we were to solve an absolute value one, we can still do this. Do you guys remember the rules for absolute values though? How do you solve absolute values? You have to do 2 cases. So first thing we're going to do is we're going to pretend that it's equal to 0. Just pretend it's equal to 0. Case 1. Literally do nothing. Just do x plus 3 equals 0. Well, that means x equals minus 3. Okay, this is the common misconception though. Will this still be true though? If minus 3 goes in here, would minus 3 plus 3 give you 0? Yeah, it would still. So that's not how absolute value works. The answer can still be negative, but when you plug it back inside, it still actually works out. That's case 1. Then we're going to do case 2. Remember how to do case 2?
You flip all the signs.
Yeah, so I'm going to make a negative x minus 3 equals 0. Negative x would then equal 3. So actually this works out the same way. X is negative 3 as well. Okay, well I guess we have 1 critical point now. So the last time we actually had no critical points. Here we do have a critical point again. I can throw negative 3 on there. Should I fill in the dot around negative 3?
No.
No, because it's we're less than simple. Okay, so let's test some values. We need to pick some values that are on the larger and smaller sides. So 0 is the best one to pick. 0 plus 3 is 3. Absolute value 3 is 3. Is 3 less than 0? No, it's not. Which means that if 0 is not true, then none of these values here, none of those actually work. So here's hoping the other side works. Pick a number that's lower than 3, like say negative 4. Negative 4 plus 3. You do negative 1. But then that is what you'd absolute value. Negative 1 absolute value would give you 1. Is 1 less than 0? Actually, no, it's not either. There is no guarantee that it has to be one side or the other. In this example here, actually neither of the sides worked. This is a good example of, wait for it, there is no answer. No. There is not a single value here that would work. By the way, I want to kind of demonstrate something here. The absolute value of x plus 3, if you were to actually plot that, it would be right here. If I were to ask you where that graph is less than 0, it's not. Okay, one more thing here. I need to show you the other notation for this. So you could basically write out there is no answer, but there's actually another way of doing it that I can finally show you now. It's written like this. Your domain is known as the empty set. What you do is you put a couple of like funky looking brackets, the little curvy ones there, and you either put a 0 through it, and what that implies is that not that the answer is 0, it implies that there are no answers. Okay. Or the other way you do it is you say the domain is the curly brackets, and you literally write nothing inside of it. And that's another way of writing it, where rather than someone mistaking the answer for being the number 0, because there's literally nothing there, that's your way of saying, what's your answer? And you don't even answer. Does that make sense? So those are some other notations you'll see as we go along in math. Well, they don't have to. Depends on where the absolute value graph goes. For example, if you had an absolute value graph that was like this, and you kind of moved the vertex around a little bit, because you can, then that might not be true. Okay, let's do some more examples here. Here's some more stuff about interval notation, which I've kind of been hinting at. If your number line, say, went from 0 to 4, closed circle at 0, open circle at 4, Jake? Nice. You would write it as square bracket for 0, because you get to include 0, comma, curly bracket around the 4. But I'd like to add one more thing. Can you guys write D next to these? Just to make sure that it's very clear that it's not a coordinate point. Because some kids, they might just think that it's 0, 4, and they might think that that's actually like a point on a graph. So convention is that you actually don't have to. I'm just going to ask that you do because it helps keep it clear. There.
Do we have to do the range with these things?
Yeah, if your variable was with y's instead, then you could do the same thing. Okay, let's try this one. Let's go crazy. Okay, so we're kind of putting this all together now. How do we solve this? Well, first things first. Ignore the greater than or equal to sign. Just make it an equal sign for now. We'll come back to it. If you FOIL this out, you get x squared minus 2x equals 4x plus 3 minus 6x squared plus 3x. So I FOILed it all out. I threw an equal sign in there. Okay. Yeah, bring everything to one side. Not that there's a right answer, but I do have a preference myself. I like my leading coefficient positive always. It's just my nature. Which means when I look at this here, see how the negative 6x squared is on this side? That means for me, I'm bringing it all that way. You don't have to, but that's just my preference. It means I'm going to have 7x squared. Let's see, 4 and 3 is going to be 7. So when I bring 7 that way, it'll be negative 9x, I think. And when you bring the 3 that way, you'll have minus 3. Well, this sucks. So, quadratic formula. Negative 9 plus or minus the square root of negative 9 squared. Minus 4, 7, negative 3. All over 2 times 7. Okay, that'll be a 9, and that'll be a 14.
What if I raise the decimals?
Then we're going to leave this an exact value.
1.560373756 and negative 0.274659469.
Okay, so what I'm going to do is I'm going to take what you wrote there. Can you read them off for me again?
1.560.
Close enough, 1.56.
And negative 0.2746.
Okay, but whenever I write these numbers down though, I'm not going to write the decimal numbers. I'm going to write 9 plus root 165 over 14, and I'm going to write 9 minus 165 over 14.
What's 14? Let's say 17. You got a minute after school?
Yeah.
About something up here.
Yeah. Okay. The only reason why I'm going to suggest we go to these values here is that'll give us an idea about whereabouts on the number line they fit. Because if I didn't actually find what these are as decimals, I'd have no idea what they mean. So now I have a rough idea. One of them is at about 1.56. I'm going to call that 9 plus root 165 over 14. And then you'll have the number 1 and the number 0. 2 will be somewhere here, and 3, something like that. And then the other value was negative 0.2 something, so it'll go right about here, and that's 9 minus root 165 over 14. Negative 1, negative 2, negative 3. So far, so good. Okay. These values right here, should I fill them in or not? This time, yes. Why? Because we'd have a greater than 7 here. Okay, last step. We just need to do some test points. So for the test points, just pick some values. I'm going to start with 0, because that'll tell us the in-between portion. And then I think I'm going to use the number 2, and I'll probably use negative 1. So let's try 0 first. If you're a 0, well then it really doesn't matter what any of this stuff is, that's all 0. If you're a 0, you're gone. If you're a 0, it doesn't really matter what any of this stuff is either, that's all. So is 0 greater than 3?
No.
Okay. Sometimes what I do, by the way, just my personal preference, is I just put an X here just to indicate that that's not where we have answers, just so that I'm clear on that. That's just my personal opinion. Which means that it's pretty likely, but it's not guaranteed, but it's possible that we could have answers either on the bigger side of this or the lower side of this. So let's test the number 2, for example. Erase this and try again. So this one's harder. 2 bracket 2 minus 2. Okay, 2 minus 2 would be 0. Times that by 2, this whole side's 0. So I guess we're back to 0 again. For this one here, you'd have 4 times 2, that'd be 8. You'd add 3. This 3 times 2 would give you a 6. That 2 times 2 would give you a 4. 4 minus 3 would make it 3. Is it able to follow kind of how I'm pulling this off? So I would say that 6 times 3 is 18. So you're going to do 8 plus 3, which is 11, minus 18, minus 7. Is 0 greater than minus 7? Okay, so that means that these answers are true. So I will then draw my arrow going this way, saying yes to them. That work? And then I go and do the exact same mess with a number that's lower than 9 minus root 165 over 14. I think that minus 1 is going to be the best option. Okay, minus 1, minus 1. Minus 1 minus 2 would give you minus 3. Times minus 3 by minus 1 means this side here is 3. Times this one by minus 1, you have a minus 4. You have to add 3. If that's minus 1 now, that makes all of that like plus 3. And if that's minus 1, 2 times minus 1 is minus 2. Minus 1 more is minus 3. Plus 3 times minus 3 was giving you like a minus 9. Minus 4 plus 3 gives me minus 1. Minus 9 more, I think you get minus 10. By the way, if you need to, use your calculators. Kind of doing most of it in my head. Is 3 bigger than minus 10 though? Yes, it was. So we have answers over here as well. I haven't done one of these with you guys yet. In the scenario where the answers go that way and that way, but they have a big gap in the middle, here's how you write it. And I think I showed you this yesterday. You're going to say it goes from negative infinity all the way up until 9 minus root 165 over 14.
And you put a U.
Good. And then you put a U. The U stands for the word union, which is a math symbol we have for whether it can be this or this. And then we re-pick it up again on the other side. On the other side, we can include 9 plus root 165 over 14, and you keep going all the way until positive infinity without using the curve bracket. And that's how we write this. Gross. I'm not going to test you on this a lot, because this is really not the point of what we're doing here, but this is actually really important. We use they test this on the diploma a lot next year. where they use this funky notation. So I just want to introduce you to the concepts of like what a U means, what the curl and the square brackets mean, and how that works. Just so you guys are aware though, this is not going to be a big part of what I test you on. Okay. It's just not that important yet, if that makes sense. I'd really rather focus on your quadratics, your reciprocals, and your opposite values. Does that make sense though? At least some? Okay. Second thing. So I kind of promised that there were two parts to this lesson. The first part is what if you only have x and only have y? The second part of it is, well, what if you have an equation with x's and y's? How do you deal with that? Okay. So what ends up happening here is your solution is also drawn as like a diagram. But what you end up doing is you shade an entire side of a graph instead. What you'll do is you'll draw in your graph, and then you'll shade either one side or the other side. And my preferred method is something called reverse shading. Okay. What you do is you shade where the answers are not. So according to this graph right here, this point right here, that could work. This point right here, that could work. This point right here, that could work. But this point down here, that wouldn't work. Okay. And you do the same sort of thing. You use a test point. So, let me show you how to do an example. Here, you see how I've thrown a graph on there for you? You're not going to graph on a number line. You know how a number line is in one dimension? Well, if I give you x's and y's, you have to do the x and the y dimension. You can't just do two number lines. You have to draw like a graph. Honestly, this is actually easier. I promise you. You'll like this one better than the last one. To do this, all you gotta do is graph y equals 2x plus 1. That's all. So go to your graph and do y equals 2x plus 1. The graph looks roughly like this.
Then you put the shade button on your
Yeah, now what's going to happen here is we're either going to shade the left side of the graph or the right side of the graph. We just need to figure out which side to shade. So all you do is you pick a test point. I'm going to pick the test point 0, 0 in most cases, but just to illustrate how this works, I'm going to pick a different point. I'm going to pick a point like, say, right here, the point 3, no, it's not 3, 6, 3, right? Because you have to have an x and a y. Well, then what I do is I go back to the equation and I plug in those values. We have to plug in x and y values, right? So you plug in 6 and 3. Is 3 going to be greater than 2 times 6 plus 1? No, it is not. Now here's my preferred method though. We're going to reverse shade this. So you shade where the answers are not. So since this is not where there's an answer, you're going to shade this side over here, thereby implying that any point right here on this side of the graph, this point should work. This point should work. This point should work. There's actually a reason why I prefer reverse shading. If you ever have to shade more than one graph, like for example, let's say you put a second graph on here, and you reverse shade where the answers are not, what you're essentially doing is you're narrowing down where the answers aren't. If you put on like multiple graphs, and you shade where the answers are not, the region that is not shaded is where your answers happen to be. Think of it as like selectively narrowing it down. Does that make sense? So that's why I prefer to actually shade a linear in one-dimension number line, but I reverse shade a two-dimensional one just in case there's more than one graph we do at the same time. So that's it. That's your answer. You draw me a graph and you shade the side it's not. And then you, if you wanted to, you could draw me an arrow and say, here are some answers. You don't actually do that. But any point on this side over here should be valid. So let's try the next one. Y needs to be less than this stuff here. So graph x squared plus 3x minus 4. Graph this guy. Looks roughly like this. Okay, now I'm actually going to use 0, 0. I should have done it last time, except 0, 0 was really close to like where the line was. Hopefully you guys will agree 0, 0 is definitely on the intersection, right? So if I plug in 0 here and 0 there and 0 there, Is 0 less than -4? Is this 0 less than 0 plus 0 minus 4? No, 0 is not less than -4. So should any of the answers in this side of the graph hold true? No. So by reverse shading, we'll shade all of these. What that should mean is, like, say, this value right here. This one over here would be like, say, 8 and 0. 8 and 0 should be true. Let's try it quick. If I plugged in 8 and 8 and 0, hopefully you'd agree. 8 squared is going to be a big number. 3 times 8 will only make that even larger. Then you subtract 4. I don't actually know what the number is, but it's a pretty big positive number, right? Well, that's bigger than 0, isn't it? So therefore, this is a point that should work in the x and y dimensions. Okay. One thing I may ask you guys to do then is I may tell you to do this graph and a second graph. So I might ask you to put a linear graph on here with it. So for example, now that you guys know how to shade these things, if you went here and shaded, see that kind of shades that section there?
Wow.
Oh, that's kind of cool. Well, then I could give you a second one where I say, like, what was the last one we did? 2x plus 1. And now I want you to shade the lower side of that graph. Then if I asked you where are there answers for both sets of graphs, well, then there's answers only in this little section over here. And that little sliver right there, by the way, would also work. So think of it as narrowing it down. Complex computer algorithms actually do this, where they want to try to, like, say on CSI, they want to narrow down a suspect. Okay, now I know this is kind of not a great comparison, but like first they want to narrow down and find, well, it has to be a man. Well, here's a graph. Everybody on that side, you're out. Now it needs to be a man who's taller than 6'1". Well, now you guys are out. Now we need to find someone who has blue eyes. You guys are out, right? And eventually you narrow it down to the spot where there's really only like a few possibilities left, and you can search those. Does that make sense? So you could draw a graph and you'd say, well, we want it to be here. Now we've taken out all the women in the world. Now we've taken out all the short people in the world. Now we've taken out all the people who have blue eyes. Now we've taken out all the people who are right-handed. Well, it needs to be somebody in this section here. And you've narrowed it down. Yeah, actually I just described myself.
Oh.
Anyways, you guys get the concept? Okay, so that's what I've got here then. I need you guys to be able to do a system of inequalities. So why don't we try this one? So just do them one at a time. Do y equals x squared plus 3x minus 4. Graph the guy. How bad on time am I? I got a few minutes. This is why I want you to start with dash 2's. Okay, so you're either shading the inside of the parabola or the outside of the parabola. So pick a value. My suggestion, 0, 0. If you plug in 0, 0, and 0, isn't this the one we just did? Oh, never mind. So we just did this one then. So let me see if I can just combine them then. That line went through there like that, and we shaded this side over here.
Oh, I understand.
These are the two that we just did. So if I were to ask you where are there answers, there are answers in this little section here, and there are answers in that little section there. Those are the two places where you could find some valid solutions when we sketch both graphs at the same time. I lost you. I went too fast. Okay, one of them was supposed to be what, 2x minus 1? Because one of them was supposed to be shading this side right here. And then the other one was shading the inside. So if you put them both together, this takes up this entire half of the graph. This takes up kind of the middle section. So you're left with one little sliver sitting right here, and you're left with an open section. So here's your summary. Inequalities then, if they're in one dimension, either x or y, draw them on a number line. Those are the harder ones, because you actually have to solve them algebraically. Inequalities with two variables, you graph it, and you shade where it's not. One last thing. You know how you have an open circle and a shaded circle to illustrate between whether it's greater than or equal to? We actually also have a convention on these graphs right here. If it is a dotted line, it means it is not or equal to. If it is a solid line, it means it is or equal to. Does that make sense? So this one right here, see how they've used dotted lines? A dotted line is a way to illustrate that this is y is just less than 2x squared, like that. If you put this guy right here, then you wouldn't use a dotted line, then you'd actually fill it in with a normal line. I'm not going to assess you on that, just in case. Okay, but just so you know the convention. If you ever see a dotted line, it means that it is a less than symbol, not a less than or equal to symbol.
I've learned so much today.
Awesome. Okay, we're done our unit. Guys, we're almost done the course now. Turning off. Well, to be fair, it's December next week, isn't it?
Oh yeah.
Did you guys realize that? It's December next week.
Merry Christmas.
No kidding, eh?
She probably is. That's what my mom wants to do, so now it's gonna be like, she's so excited. She's so excited, like she can't.